there. Uh, so you're on.
Okay. Let me share my screen here real quick. All right. Hopefully you can see a blinking cursor there. I don't really have any slides because I was up until almost midnight last night just working on my script, as luck would have it.
We
But
do
I
have
do
a
think that
blinking cursor. We do have
excellent,
a blinking cursor.
outstanding. Um, so what I would like to talk about today is, well, first, of course, who am I? My name is Sam Falvo. I used to be a significantly more prolific presenter here at SVFig many years ago. Then I got married and life happened, and all sorts of things seemed to work against me to be able to contribute here. But I found a way this month to do it, and by the skin of my chinny chin chin, I came up with a what I think is an interesting presentation that talks about the utility of Forth, especially as a natively hosted operating system environment. Um, and but before I go there, I want to lead in with this. I was watching a 4 hour long, rather grueling interview with none other than Ken Thompson, the inventor of Unix. Um, and you'll find out why this is significant, I think, a little bit later in the presentation. But this is Unix with a CS, not with an X. Okay. This is back in the days when he was working with a PDP-7 with 4 kilobytes of memory or 4 kilowords. I can't remember exactly which he said. Regardless, it was so small of amount of memory that you really didn't have any resources available to do anything with it. He was just coming off of the Multics project at the time, and AT&T had just backed out of the Multics project because it was a major time and resource sink. But Ken was still working for Bell Labs, which was an R&D group, and Ken wanted to continue, playing with computers because it was an interest of his, and in particular, queuing algorithms for disks and drums. But he also wanted to play games on computers as well, right? So as you can imagine, as he's working on these algorithms, it wasn't too large of a leap to think, I've only got 4K of memory available, but I've got this huge amount of storage, or at least relatively huge at the time. Um, I just need a way to tell the computer to run this program here or that program over there, right? So he eventually added what today we would call a fairly simple file system. And eventually, as needs arose, obviously he needed a very simple shell interface, some kind of command line that allowed him to direct the computer to run his programs. But there was, still one fairly small problem, I guess. You can't play games while you're running your queue simulation, or vice versa, right? So Ken took it upon himself to, uh, solicit resources at Bell Labs, and eventually managed to up the memory, I would imagine, and added multitasking to his small little project, which allowed him to run queuing simulations at the same time as him playing games. And in a way, it kind of fed into his research because if you're in a multitasking environment, that's a much more realistic amount of load to apply to these storage devices, right? So it actually worked to his benefit in terms of researching disk queuing and things of that nature, and so on and so forth. Eventually, it came to, other people at Bell Labs finding out what he's doing, and they're like, hey, man, can we get time on your computer? And he was like, why do you need time? Just log in, right? So he added terminal support and multi-user support. But the interesting thing is that this all kind of evolved organically from what is essentially what today we would basically call like an RC 2014 computer, something that's, very, very small, very, very limited in terms of resources. Eventually, though, there did come a time when they were just running out of space and compute ability, and they had to update to a PDP-11. And here we actually had enough resources that you could actually legitimately have multiple people on the system at once. Now, up until this point, you had so little memory that when you swapped programs, you were swapping between 4 and 8 kilobytes of memory, which is about today roughly the size of a single page, right? One or two pages. With the PDP-11, now you had multiple people working together, but you had no memory protection until just now. And that memory protection was in the form of a base limit register system. In other words, it used segmentation, not paging, right? And even today, there's still a living fossil of a system called S-break, which is used to adjust, the limit of a particular process. So basically, the point that I'm trying to make here is that Unix was not originally this incredibly complicated behemoth that we know it today, right? Linux, FreeBSD, Mac OS, these are all gigabyte operating systems, which require, gigahertz of clock speed in order to maintain any degree of usability. And it didn't start that way. It was actually very humble. The original Unix was, I would argue that the project called Fuzix, Fuzix, I would argue that that's actually more complicated and more resource hungry than what the original Unix started out to be, right? Um, and so basically, when you also you can see similar trends in other operating systems as well, right? So CPM eventually evolved to NPM for multitasking, eventually acquired network and true multi-user capability with MPNet. Um, DOS, of course, evolved into Windows NT through a long chain unto itself. And basically, my this kind of leads me to a law, which is all operating systems evolve into multi-user, multi-processing operating systems given enough time and interest, right? Um, so how does all of this relate to Forth? Well, I mean, I think it bears repeating that many Forth systems are strikingly similar to the original days of Unix. Single user, single process at a time, with or without multi-threading, extremely comfortable on machines of 8 kilobytes of memory free or less. And it just follows that, you throw more resources and interest at Forth in a similar manner, eventually you're going to end up with, a multi-user, multi-processing system, right? And the answer is yes. It actually already happened. The NRAO radio telescope control system was, in fact, a multi-user, multitasking system that actually supported numerous terminals, even supported graphics, if I'm understanding correctly. And so, long story short, if you've ever wondered why in a multi-threaded Forth environment you have a distinction between variable and user variables, that's where that comes from. User variables used to be a storage space that was allotted to a particular logged on user, right? So, so yes, this actually even happened to Forth at one point. So the question now is, if you have a Forth operating system, something that's hosted natively, one of the how do you use it comfortably? Because one of the problems with Forth is that it is unbelievably literal. Um, if I wanted to copy blocks, from one range of storage to another, you might use a program such as this, BCP here for block copy, right? I give it three arguments, tell it what block to start from, where to put it, and how many blocks on the stack, right? And we just have this loop here that basically goes through. And for each block, we do a move operation. We mark it as updated, and we just uh, do the transfer that way. A remarkably small amount of code, extremely fast, however, extremely single purpose as well. Now, in the real world, when you're using operating systems of other types, Windows, Linux, etc., you're going to find that there's actually a plurality of modes of copying things, right? And typically you'll have one copy command that is capable of doing a number of these variations on the theme, right? And so when you have these variations on the theme, to do the same thing in fourth, in the obvious fourth sort of way, you have n basic operations and then m variations. You have n times m programs that you need to remember, you need to name, and you need to document how to invoke them, and so on and so forth, right? So I'm thinking instead of doing that, why not support a little bit of incidental complexity, right? The issue with complexity in fourth is, well, complex. It has a history, of course, but I think it goes without saying that what we most revile is unnecessary complexity. I would make the argument that incidental complexity is okay, as long as it can be reasonably justified and it solves a particular problem. And I'm a person who likes to use fourth as natively as possible if I can. I remember very fondly using Pygmy Fourth as my daily driver for an operating system for many, many years. But the problem is, whenever I'm in a block environment, I have a number of things that I would like to do with these blocks that there's no convenient way of doing them, right? So one of these is to copy a range of blocks into or out of memory. Again, easy enough to write if I need it. But the thing is, you have to write it. You have to remember to write these tools, right? Number two is treat a range of blocks as a possibly named temporary file. This problem came up when I was writing Unsuitable, my blogging engine many years ago. Number three is to copy or move blocks from range A to range B. Again, we've got that special purpose block copy routine up above. And number four is how do you create and maintain backup files? Not just local files on the local file system, but also in block storage as well, right? And five, this one is my most recent issue. How do I do revision control using code stored in block storage, right? How do I make use of Git, for example, with source code stored in block storage? So my feeling here is that I have a legitimate case for breaking Chuck Moore's rule of not generalizing and coming to the conclusion that yes, maybe I think a general copy routine would be the best way to go about doing this. Now, my script here, I'm kind of glossing over my script for time reasons, but you'll notice that I've embedded a lot of code into my script here, which I'm showing. So I'm just going to skip down to the bottom. I'm just going to briefly explain this. But if you want access to the actual code, I'll post a link to the GitHub repository. I'm sorry, Source Hut repository, similar to GitHub. And there you can take a look at and play with the code yourself as well. But here, for example, I've just embedded this for documentation purposes. So the idea is to call a word copy, right? And we give it two parameters, a data source where we're copying data from and a data sink where we're sending data to. And it returns an IO result, which you can then use with throw to handle any errors if you need to. That in turn makes use of this parenthesized copy, which actually is the data pump. What it does is it reads a block of data. It Allow me to rephrase that. It reads a buffer full of data, or tries to as much as possible. Make sure that we receive at least 1 byte. If we receive 0 bytes, then we know that we've reached the end of the input stream and we abort the copy operation from there. And you can see that when we look at these words up here, read and write. If you study these in detail, these basically, as you can see here, um, these words basically behave in a Unix-like way, right? So you ask it for a certain amount of space, and it will read, in this case, the size of a buffer. And what it does is it returns the actual number of bytes read, right? So it's very POSIX-like in that sense. Same thing with write. We want to give it the amount of space that we actually read, because we don't want to write data that doesn't exist. And it returns a value that says, oh, I've written actually this many number of bytes, right? So in this sense, read and write kind of behave like a POSIX functions of their same name. And what we do down here is we just make sure that the values that we're getting match our anticipation. So in the case of reading, we want to make sure that we get a non-zero amount of data. Otherwise, the copy operation aborts cleanly because we've reached the end of the input stream. Likewise, if we're writing, we want to make sure that we actually write the full set of data that we received. Otherwise, we surmise that there's no space left in wherever we're sending the data to. And this is essentially the entirety of the copy operation. It's very simple in the sense that it does one thing exactly. It does one thing extremely well, but how it does it is kind of maybe a little bit more complex than what, say, Chuck Moore would appreciate, right? Because up here, you'll notice that we use RD and WR, and also DR for dropping a particular source or sink. We use these words to actually perform the I/O, right? This is where the rubber meets the road. And you'll notice that I do vectored execution. And this is how polymorphism in Forth actually works. If you were to examine the source code to defer, for example, you'll notice that there's a fetch execute in it, right? If you'll notice, like what Bill Ragsdale posted earlier today with the Win32 object-oriented programming. If you examine the implementation of that, you're going to find a lot of fetch executes, right? And so basically, this is all just polymorphism here. And what I do is I'm essentially accessing memory, a table, if you will, of execution tokens that allow me to that basically is my interface to working with the copy routine. And there's 3 components to it. One is a reader, which is responsible for sucking data into memory as much as you can. You have a writer, which is responsible for pushing that data back out to somewhere as much as you can. And then when the copy operation is done, you want to make sure you clean up resources, right? So I have what's called a dropper. All this does is basically is a way of communicating to your sources and sinks that says, hey, I'm done with you. Go ahead and close files, go ahead and clean up resources, whatever, right? And so in that way we try to be as clean and efficient in memory as possible. Let me give you an example of this. I'm just going to kind of, well, let me start here. Basically, this is what it looks like in memory. That your sources and your sinks are basically objects that you create in the dictionary, but they have to have this particular layout. This, what I call a V table, which is a common term. It's actually taken from C++ because it works the same way as C++ V tables. Basically, what we're doing is we're allocating space in the dictionary with these sources and sinks that, kind of serve the same purpose as file control blocks in CPM, right? And but the thing is why did my timer disappear on me? Why? There we go. Um, and so basically, the only element of these structures that is well known to everyone is this vtable pointer, which in turn points to, your table reader, writer, and dropper, and so forth. Now, it should point out that multiple sources of the same type all share the same vtable, and you can have as many different types of sources and sinks as you want, right? So here's one that actually just is a thin veneer over ANSI forth file IO. This is what allows me to copy files in the local file system. And you'll notice that I have two constructors down here because the semantics of how open file versus create file work, I have a need for two constructors, one of which builds a control block for existing files, and you have one here for creating new files. But they both share the exact same vtable, because once a file is open or created, then they behave exactly the same way. So in this case, read file already basically does what we want. So it's a very simple one line definition. Writing almost does what we want. For some bizarre reason, write file does not give an indication of how many bytes it actually wrote. So I have to use file size to surmise that. But unfortunately, it is a more complex definition, but still well within the realm of understandability at a glance, right? And that is all it takes to couple this system with the local file system. We can also do this for blocks, which is uh, uh, my desired and preferred environment. This is a lot more complicated, and you're going to see this mainly because with blocks, you have to implement the file, like literally the file control block and the way that it behaves. So I'm just going to skip this as it says up there. These are all just private words. The methods down here indicate why, though, because if you'll notice that we have to do, when we do a transfer, we start out by doing whole block reads, if possible. And then if not, we do sub block reads, basically anything less than 1024 bytes. And same thing with writing as well. And both of these, they have very similar code structures, as you can see up here. But you'll notice that there's that word account. And you'll notice that we need to keep track of a lot of stuff, right? Sometimes it's not just a simple wrapper. Like we need to record where within the block we currently are reading from or writing to. And you'll notice here that I've defined read and write, RD and WR. These are different semantics from the RD and WR in the copy code. This will become important a little bit later. But for now, just realize that one of the advantages of writing code this way is that other than your constructors, everything is private, completely arbitrary. As long as everyone agrees where that vtable pointer is, everything can be named however and wherever you want. For smaller forth systems where you can do headerless dictionary entries, that means that the bulk of this implementation can be completely headerless. The only things that need headers are your constructors like this. And that's it, right? So that can actually save quite a bit of space. So this is how it would typically look, right? If you were to use this. So if we were to copy the contents of a file into block storage, this is what it might look like on the command line. So you give it the name of the file, you tell it it's a read-only file, and then you give it a range of blocks, and you create the block sync, and you tell it to copy, right? So not quite as simple to use as CP on the Unix command line, Um, but we're getting there. I mean, compared to the alternative where you basically have to write all this code yourself, um, it's a vast improvement over doing things manually, right? The problem is if we do this, we're treating the block storage as a binary resource, right? We're just reading and writing from block storage as it is. But if we're reading source code, then the issue is there's going to be control characters embedded in the blocks, and it might not alter how Forth interprets a block when you load it, but when you list it to the screen, it's going to look like absolute garbage, right? Because it's going to be it when you execute list, it doesn't anticipate control characters in the listing. So what I needed to do is I also needed to define um, this resource here, which is basically a filter that takes that resource as a parameter and wraps it in a way that allows copy to natively understand what fourth source code looks like in a block. So in a sense, we've created a system of filters. Now take a note that this filtration is happening on the output side, not just on the input side, right? So this is already a system that already is kind of giving Unix pipelines a run for its money, right? Because not only can we filter on the input side, but we can also filter on the output side as well, which is not really something you can do in Unix without additional custom written code. And we can actually go exactly the opposite way as well. Let's say that you're using for block storage and you have source code in block storage arranged with shadow blocks, right? So that means that all your even numbered blocks contain code, all your odd numbered blocks contain documentation. Well, how do you separate that out? Like, let's say you want to disentangle that for, you want to commit those independently to Git. Well, you can actually do that, right? So this particular parameter here that I've got my cursor on, that is an increment for for the block sources and sinks. This basically says after I've done reading a particular block, how many, what number do I add to get to the next block in the sequence, right? So I can basically say starting at block 100 for a length of 20 blocks, going every other block, I want to wrap that into source code source, and then I want to write this as source.fs in the local file system, and I can copy that. So using the same mechanism as any other copy, I can now import or I can export source code from block storage or vice versa, re-import it from local files into block storage. And this just demonstrates that the way to do that is to just swap the order of parameters. Let's see here, and this is the source code wrapper that does that. Um, I've got what seems like 2 minutes left, so I'm just going to go ahead and kind of skip over that. But basically, you can see here in the write code, um, I've got the logic that allows me to look for carriage returns, or I'm sorry, line feeds to be more specific. Although in real world implementation, you'd probably want to parameterize that. But it looks for that, and and it does the expansion into spaces so that you can actually write that back into block storage in a meaningful way, right? Um, and again, there's your constructor code, and I believe now is a good time to show a little bit of a demo. Okay, so what I'm going to do is I'm going to load up all my stuff. Yes, there's a bunch of stuff that's redefined. That's okay. Let's test that address. Okay, so this is the definition of what's in test.fs, and as you can see, it is basically a already exported set of blocks, but it's formatted like a plain regular text file. And you can tell because if I jump to the end of the line on this, right, I can't move beyond that. So that's literally the end of that line. And just to prove that once more, I'm going to move my margin there to 64. And this just goes to show that everything is 64 characters or less. And if I turn on line numbers, you'll notice that everything is nice block, arranged on block boundaries. So this should be nice and clean to import. So what I can do is I can say, I want to read from test.fs. It is read only. And I want to write this to block 10. We don't care about how many blocks there are because that's dictated by the source, not the destination, at least how I've written it so far. I want to go, just for grins, I'm going to go every other block just to show that it works. I'm going to make this a screen. I'm going to copy, and hopefully everything worked great. Okay. So I'm going to flush the buffers out. So now we can see we have right here, we have a new file called blocks.fb, right? So this is what Gforth uses to store its blocks. If I use a hex editor in that, oops, and we go to block 10, and we see, you'll notice that there's no carriage returns. Everything is all padded out with spaces, right? And you'll notice also that we're skipping every other block as indicated by the null values there, right? So this allows, already we're seeing that we can do some pretty good general purpose processing with this. We can also go the other way. I think that's 5 blocks, I believe. Doesn't matter. Right. We're going to make a new file. Okay, that one says it aborted. I think this would still work though. Let me just double check. No, okay, I've got a bug somewhere. But if we get rid of that, but you'll notice that it properly terminates the line right where it needs to properly terminate. So why it's not handling multiple lines, I'd still have to debug that, but at least we see the basics of how this thing is working anyway. See if I can get back to where I was. I think this is. This is close enough. Yeah, there we go. Show demo. Okay. So basically, what did we create here, right? So, well, because of the way that I wrote the code, I basically have an object model that's similar to G object or C++, right? I don't need something like Neon or Yerkes or anything like that. I can actually just write this and get it done with plain vanilla for it. Plain vanilla for it. I don't need anything. However, recognize that a lot of that code up there is boilerplate. Okay. So if you have an object system available, by all means use it because that's what it's there for, right? It's there to hide, not hide, I would say more to automate the construction of that boilerplate so that your object dispatch will work correctly. The other thing that we have is a copy command that is infinitely open-ended, right? We've seen how we can write filters. We've seen how we can write sources and sinks. So what is a compiler if not a filter of some sort that just accepts ASCII source code on the input and spits binary object code on the output, right? It's conceivable. I don't recommend this, but it's conceivable that you could write a compiler, a C compiler, that accepts input and is driven from this copy command. It would be ludicrous for you to do this, but it's doable, right? Um, that's how open-ended this particular tool is because of this standard interface that it works with. Some people here might be old enough to remember working with OS 360 or OS 370, or as it later come to be known as MVS, more modern ZOS, right? You may be looking at a structure like 110 to make block SS, and in your brain is like, I know I've seen something like that before. Yes, you have, because it's the exact same thing as the JCL DD statement. What it's doing is it's declaring a data definition. We're giving it information that allows it to create, like I said, a file control block that the system can then use through an abstraction to determine how to fetch and store data, right? It's doing the exact same job. And finally, we have a means of filtering and processing data that potentially is more powerful than stock out-of-the-box Unix. And I want to be clear by what I say by out-of-the-box Unix, because you can always write custom C code to do the same or similar things as what we're doing. T is an example of just such a program where it takes data off of standard in, spits it out on standard out, but it also spits it out on other files and or file descriptors as well, right? So T is an example of an outbound filter like that. But in the case of what we have here, we can actually write data sources that accept information from large amounts of fan in, right? So in other words, we can write multiplexers, we can write concatenators, whereas with the output, we can kind of do the same thing. So here's a logical block of what I was describing up above, right? We've got two sources, in this case blocks. We run it through a multiplexer. Now, this is a different way of achieving the same goal as what we demonstrated earlier. We could run it through a multiplexer that is designed to alternate or interleave blocks from one of two sources. The copy command is your pump that sends that data out. We then have a fork or a T that basically sends the output to another destination block stream, as well as at the same time a destination file in the local file system, right? So one copy command can actually grab data from multiple sources and update multiple destinations at the same time, and that's some of the capabilities that we've created. And all of this, by the way, if you were to do a size calculation on this, on a 64-bit G4, all of this code, all in memory at once, takes up a whopping 12 kilobytes. If you were to run this on a 16-bit fourth, I estimate it would take no more than 3 to 4 kilobytes at best. And since I'm planning on starting some new projects that are going to be running on a Commodore 64 here pretty soon, mostly written in fourth, I intend on using this to my advantage, particularly since once you run fourth, it's very difficult to get out of it, since the 64 has no Unix-like operating system, right? So being able to run fourth as your native host development environment implies the ability to do system administration tasks conveniently. And in order to do that, you need a set of data sources, sinks, and commands that work with them so that you can make your life easier, right? So my argument again, is if you're going to use Forth as a hosted operating system, this is the type of incidental complexity that I think is justified. It solves a very real need for me, at least. Um, and I'm not saying that you have to do it this way, but the idea of exploiting some manner of polymorphism is more powerful than I think most people give it credit for, especially when it comes to command line operations. So anyway, I think that's all I have. Again, I've got this script here that's going to go up. I'll send that out on the generalities mailing list. It'll also be up on my source hub as well, and I'll be posting it onto my personal website as well. So, does anyone have any questions?
We are a little pressed for time, Sam. One or two quick questions.
How about this? How about if you have questions, send me an email directly, and I'll be happy to answer.
I definitely have comments, but since it falls over into my time, but definitely extremely interesting. Sort of a uh, uh, my notes. Let me see. I might as well share my screen.
So
Um,
with that, it's now Bob's time. So thank you, Sam, and put your email address in the chat for conversation.